So we've got a couple interesting examples of situations where we can apply this pigeonhole principle. So in this first one, I want to show that if you pick n plus 1 numbers from the set of positive integers less than or equal to 2n, then at least one of those pairs has to have a difference of 1. Right, so here's how I'm going to do this. Take the numbers from 1 up to 2n and pair them up. Right, so I'm going to put 1 and 2 together. I'm going to put 3 and 4 together, 5 and 6. Notice how each of these pairs differs by 1, right? Then I'm going to go down to 2n minus 1 and 2n. Right, so the first thing I want you to notice about this list is there are n pairs. Now, pick your numbers. All right, go to this list of numbers, integers 1 up to 2n. Pick your n plus 1 numbers. I'm going to put them over here. I'm going to call them a sub 1, a sub 2, a sub 3, so on, down to a sub n, and a sub n plus 1. All right, now think about the pigeonhole principle. The numbers you chose are the pigeons, and the numbers, these pairs of numbers on the right, those are the holes. So what I want to do is I want to pair up every number that I've chosen with the pair of numbers that it goes with. All right, so for example, maybe A2 goes to here, AN goes to here, and so on. Right, now think about the sizes. I'm putting n plus 1 objects into n categories, n buckets. Right, so the pigeonhole principle tells me that at least 2 of my numbers over here are going to have to be in the same category. So at some point, I'm going to have a second number that belongs into one of these pairs that are off by 1 digit, right? And that's what I needed to show. So what I'd like to show here is something that you probably learned maybe back in middle school as the definition of a rational number. A rational number, you'll sometimes see this in introductory classes, defined as a number whose decimal expansion either terminates or repeats. And that's fine. The definition that we've been using is the ratio of two integers. That's the more precise mathematical definition. But you do see this a lot in middle school, maybe even up into the high school level. So what I want to show is that the decimal expansion of every rational number does either terminate or repeat. Right? So what they're teaching back at those early classes really is appropriate. So let's cover the repeating case first. Let's say, for example, I have 4 divided into 10. And let's watch what happens when we do the long division. This is going to be 2 times 4 is 8. That's 20. I'm going to put a 5 here. I'm going to subtract. And once this goes to 0, it stays 0. I mean, we can keep doing this all day, right? So one option is the decimal expansion terminates. Okay. What about the repeating situation? In other words, what happens if it doesn't terminate? Well, let's look at another example here. Let's do let's do 7 divided into, and I might need to do quite a few of these before we get to where we need to be. But let's do 7 divided into 4. Hopefully I won't need quite that many. So we'll do 5, 35, and subtract, bring down the 0. So 7, that's 49, bring down the 0. Did we get 10? That'll be a 1. Subtract again, we get 30. 4 is 28. We're almost there. 2 gives me 14. And we're going to do, what, 7 times 8 is 56. And here's where it gets interesting. Now I subtract, you get 4 and bring down a 0. Notice here, I already had a 40, right, as part of the process. So now let's do the next step. I'm going to put 5 up here, 35, subtract, and you get 50. Well, look at what else happened here. Right? Here I had 50, and here I had 50. Right? So you can see once I I get to the same number, right? Once I get this duplicate here, then it's going to carry on duplicating on and on and on. Okay, so let's see how the pigeonhole principle comes into this. Let's let these numbers that I got from doing the subtractions, call these the remainders, right? So 5 would be R1, 1 would be R2, 3 would be R3, and so on. Okay, so sooner or later this starts to repeat, right? So what I have here is I have 10 possible digits for the remainder, right? The remainders have to come from 0, 1, 2, 3, up to 9. So I have a very large number of remainders. Let's say we look at just the first 11 remainders. Okay, so then I have 11 remainders and I have 9 numbers, excuse me, I have 10 digits that I have to put into those categories. Well, because the number of remainders is greater than the number of possible digits, some digit is going to have to appear twice. And as soon as we get a remainder that appears twice, this is this one down here, the 5, this is our 1 over again, right? As soon as we hit that repeated remainder, from there on, this is just going to repeat cyclically, right? Which is what I needed to show. So now hopefully you've got some idea of how the pigeonhole principle works, right? That last proof in particular um, was pretty interesting, a moderately significant point. But we can actually go further. We can actually go further than what the pigeonhole tells us. In the next lecture, we're going to look at something called the generalized pigeonhole principle, which let's just go beyond saying there has to be one group that has more than one, saying, well, there has to be at least one group that has 6 or 7 or some specific number that's going to let us be a little more specific.